So hi guys. Um, so when you study the Navier-Stokes equation, um, you the form of equation you encounter will be sorry, yeah, rho partial u by partial t plus um plus u dotted with grad u, right? And then uh, that this is equal to rho by du over dt. The big D just represents the material derivative or the convective derivative, and that's equal to minus gradient of pressure. That's the pressure force plus, if you assume a zero divergence of the velocity, namely incompressibility, uh, you will find there is a term proportional to the Laplacian of u, and plus whatever body force term you have. So this equation is so as long as if there's if rho sorry if divergence of u is not zero, for example in a compressible fluid, this term would be this term sorry, it should include that the viscosity. So this term should be a divergence of a general vis viscous stress tensor, right? This pi is a viscous stress tensor, and it's a tensor, so the divergence of a tensor is a vector, and this tensor will have some specific expression which you can derive from a kinetic theory, and I'm not going to go over that in this short video, and you can just look at Alexander Shekov-Chihin's notes about everything. But so if you replace this by that, you will find a completely general form of the Navier-Stokes equation describing the motion of a fluid. Now, there was one question about this term. So is this term completely general? Because remember that when we start Newton's second law, we find that the most general expression for Newton's second law is just the force is equal to dp by dt, right? So that also applies when you have variable mass, right? When you have rockets, you use that equation rather than F equal to ma. You can use F equal to ma, but you have to pay attention to like which a you describe, which m you describe. But this momentum, if you include the total momentum inside the derivative, everything just works better. Now, what about here? Should we include rho into this u? Is it the most general case if we bring the rho inside, or should we keep it outside? So that was one of the questions that was raised when I study the B1 course, the fluid mechanics course, and the answer is no, right? The rho should just stay there, and that's the completely general case. And why is that? Right? Why is that true? Well, I mean, this is again, this is not difficult. This is just a subtlety. But in case you you come up with this question, but feel that you need an answer, I'm going to continue the conversation and just talk through it but it's really subtle and it's not difficult either. So this particular question, to answer this particular question, there's an easy way and a more rigorous way. I'll just show an easy way first. Yeah, that's how I think about this question. Of course, the easy way is how I think about this question, because the rigorous way is it's written in the book, and of course, it's not done by myself. Yeah. So this, so what I think about this question is, remember how we derive. Like, let's just forget everything. Let's just forget this. All right. Let's just forget about this and just focus on this Euler equation. Right. So the Euler equation, rho du by dt is equal to the minus the gradient of pressure, right? And this particular equation involves, so this is the mass, this is the acceleration, and that's the force, right? Of course, everything is per unit volume, but effectively that's just a simple way of writing Newton's second law. And you will say, okay, mass times acceleration, that's not completely general. You should bring mass inside and becomes a derivative of the momentum, and then the equation should be completely general. But then in this case, in this particular case, it's actually not. So why is that? Remember how we derived this equation? How we derived this how we derived this equation was just writing down the Newton's second law, right? So how did we derive this? Well, we derived this by just writing so the integral of rho. So that's what you will encounter in third year lecture. So rho du dt by dv is equal to minus pressure times d vector ds, right? And then by divergence theorem, that's just equal to, oh, well, that's not the divergence, but it's a similar theorem. I think that's just grad PdV, right? And here this expression, this expression just shows that for a volume V we are interested in, right? For volume V we are interested in, there are pressure forces everywhere, and all the sum of all these forces will become the rate of change of momentum of that whole volume V of fluid materials, right? But in the lecture you will start with this, and someone may argue that, okay, that's just a simplification when rho is constant, right? When rho is constant, the rho u dt is rho du by dt, right? And someone may argue that, okay, that's a simplification of the rho u by dt, but and they will say, okay, the correct expression for the acceleration times mass. Okay, so the correct expression for the force of experienced by this whole volume would be rho u by dt dv, right? Is that looks better? But is this, if you want to think the most general case, right? When rho is constant, when rho is varying, and when u is varying, when everything is changing, what is the case you want to consider? Is this the most general case? No, that's still not the most general case. You can differentiate more things, right? You have three things in this integral, not just two. One is u, one is rho, and the other is dv. dv is also changing, right? Because of the conservation of mass, when rho is changing, a volume element is still changing, right? If rho is changing, this the same amount of fluid will expand, right? If rho is decreasing, or like if rho is increasing, it will contract. So we're investigating this amount of fluid. So what happens? Like what actually is the most general case? Should be this, right? Should be should be d by dt integral rho u dv, right? This is the momentum of the entire volume, right? That's just m dm u dm integral of rho u dm. That's the momentum of the entire volume, and you differentiate with respect to that. That's the most general expression for the force, right? And when you get that, interestingly, because of the conservation of mass, you will find that in fact rho dv is dm and is constant, and dm by dt is 0. So you're left with just this, right? You're left with just this. This is equal to integral rho du by dt dv, right? So in fact, this is not a simplification, but rather derived from the most general case that we can think of. And in fact, even if rho is changing, we have to use this rho. So we just don't right. We just don't put that rho inside. We'll keep it, and that's the completely general equation. Okay. So remember, I was talking about a more rigorous way of doing this, right? Yeah, just clear some space. Okay. So the more rigorous way of doing such a question is to use a theorem called the Reynolds transport theorem, and I think that's not covered in the syllabus. If you study math, you probably will learn it, or not. I don't really know. But that's just essentially a mathematical equation. It's not something that's so physical that we need to worry about. But I mean, it's worth studying, and it's not something really difficult. So the Reynolds transport theorem says, for example, if you have any scalar or vector function, let's just say it's a scalar,